In the previous videos, we studied about single random variables. In this video, we discuss about multiple random variables, joint probability density function, and conditional probability density function. We consider multiple random variables and their PDF. At times, the outcome of an experiment requires more than two random variables, either two or more than two random variables. And then in that case, at present we take the probability of a random variable x lying between a and b and y lying between c and d. That is, we are considering two random variables x and y. In that case, probability of x lying between a and b and probability of y lying between c and d is defined as integral c to d and integral a to b fxy xy dx dy. This first integral limit c to d indicates the interval of c to d for the y random variable, and this integral a to b gives us the interval of x random variable. Now at this point we recollect the probability of single random variable lying between a and b. Suppose this is the probability for a single random variable. It is given as integral a to b fxx dx. This we have already seen. So for a single random variable lying between a and b, it is integral a to b fxx dx. This is known as PDF, simple PDF. And if we extend the same definition for two random variables, then probability of a less than or equal to x less than or equal to b and c less than or equal to y less than or equal to d is equal to integral c to d and integral a to b fxy xy dx dy. This is known as joint PDF. As we are using two random variables x and y, this PDF is known as joint PDF. The joint PDF gives the probability of two random variables lying in a region. Suppose if I draw this and if I mark x here and y here, and x is varying between a and b and y is varying between c and d, and between this, if you extend the diagram like this, it represents a region. So it gives us the probability of this region, x lying between a and b and y lying between c and d. So this is the probability of this region given by joint PDF. So this is the area covered under this region, or in other words, joint PDF is the probability per unit area. And if you consider the properties, the fxy xy is greater than or equal to 0. It means joint probability density function is always non-negative, it is a positive number, like in the case of simple PDF. And then the another equation is the probability is the area covered under the probability density function, joint probability density function is unity. Like in the case of single random variable, the area under PDF is 1. Similarly here also, the double integral fxy xy dx dy is probability of x lying between minus infinity to infinity, y lying between minus infinity to infinity is equal to 1. Now we study about cumulative distribution function for two random variables. So it is indicated as fxy xy. Now it is defined as the cumulative distribution function of two random variables x and y is given as probability of the random variable x is less than or equal to x, the random variable y is less than or equal to y is equal to integral minus infinity to y integral minus infinity to x fxy xy dx dy. This is joint PDF. At this point we recollect the cumulative distribution function for single random variable, that is given as fx x is equal to probability of the random variable x is less than or equal to x, that is equal to integral minus infinity to x fx x dx. This is the basic definition for cumulative distribution function of single random variable. The same thing can be extended for two random variables. That's what we can observe here. For two random variables, it is probability x less than or equal to x and y less than or equal to y. And as there are two random variables, we have two integrals. Y value varying from minus infinity to y, x value varying from minus infinity to x. And now, here in this case, we obtained the cumulative distribution function from the joint PDF. In this case, we have got the cumulative distribution function from the single PDF. The same result can be extended, and if we differentiate on both sides, then we can get the joint PDF from the cumulative distribution function. By differentiating the cumulative distribution function twice, in this case of two variables, we are partially differentiating with respect to x and with respect to y, then we are getting joint PDF. If it is for single random variable, we already seen that fx x is equal to d by dx of fxx. So the same result can be extended to root two random variables. This is how we are obtaining joint PDF from the cumulative distribution function. Now we see the properties of joint PDF. The joint PDF is always greater than or equal to 0, that is non-negative, as it is dealing with probability. And second, the total value under the curve of joint PDF is unity, that is this integral under joint PDF is equal to 1. The PDF of single random variable is fx x. If the PDF of the two random variable is fxy xy. Now the question is whether we can compute fxx, that is the PDF of single random variable, from the PDF of two random variables or from the joint PDF. If the joint PDF is given, whether we can compute single variable PDF or not. Yes, we can find out the PDF, single variable PDF from the joint PDF. This is the equation. fxx is equal to integral minus infinity to infinity fxy xy dy. Here fxy xy is joint PDF involving random variables x and y. fxx is the single random variable x. Here one should take care of the variable. Here we are integrating with respect to y. The y values are changing from minus infinity to infinity. So if you want to obtain single random variable PDF fxx, then you have to integrate the joint PDF with respect to y from the values minus infinity to infinity. So this single random variable PDFs are known as marginal PDFs. These PDFs fxx and fyy are known as marginal PDFs. So we can compute marginal PDFs from the joint PDF. Here the PDF of random variable y can be obtained from integral minus infinity to infinity joint PDF. The variable here is x dx. With respect to x, we have to integrate between the values minus infinity to infinity. Here the x values are varying from minus infinity to infinity. So if you want to find out the PDF for random variable y, we have to integrate the joint PDF with respect to x between values minus infinity to infinity. This way we are computing marginal PDFs from their joint PDFs. Here the fxx and fyy are known as marginal PDFs. In the case of two random variables, we define another term here known as conditional PDF. What is conditional PDF? The probability density function of x given that y is equal to y is known as conditional probability. It is laying a condition that what is the PDF of x given that y value is small y. So this is the condition lying down here. That's why it is known as conditional PDF. It is indicated as f x by y within brackets x by y. How we read it? It is conditional PDF of x given y. So we can ignore this term here and simply write fx x by y. So that is given as joint PDF by fyy. If I want fx probability density function of x, then y is given, that is conditional PDF, is equal to joint PDF by probability density function of y. Suppose if I want fy given x, how we write? Is again fxy, this is joint PDF, and here in this case it becomes fxx, if I can understand the difference. So conditional PDF is defined as the probability density function of x given y is equal to y. It is given as joint PDF fxy xy by fyy. And again, as we deal with probabilities, there is always a non-negative number here, and the area under conditional probability density function is also always 1. This concept is very important. What are statistically independent random variables? If two random variables x and y are known as statistically independent, if the knowledge of x is not adding anything to the knowledge of y, in simple terms, or the knowledge or outcome of y is not adding anything to the knowledge and outcome of x, in this case we call these two random variables as statistically independent. Now we go for the definition of conditional PDF. This is conditional PDF of x given y is equal to y. Now in this specific case, as the knowledge of y is not giving any information about x, that is simply equal to fxx. Now we will rewrite the equation for the conditional probability density function of x given y is equal to joint probability density function by fyy. This is the basic definition for conditional probability density function. Now if x and y are statistically independent, then this becomes fxx. Now this is equal to this. Therefore we can rewrite the equation in this way. And we expand, then the joint probability density function is given as the product of marginal PDFs. We know this is known as marginal PDF of y, this is marginal PDF of x. So the joint PDF is given as product of marginal PDFs provided x and y are statistically independent. So in this video, we considered multiple random variables, and we also observed what is joint PDF, and then we have conditional PDF, and finally we have seen and defined what is statistically independent random variables.